Some of you have learned linear algebra, but we need to make sure that all of you have this knowledge after this course. So the following slides might be more straightforward or simpler for some students, but for other students, it's your best chance to learn matrix. And our goal is that all of you will know matrix algebra by the end of this lecture. And we will start with some specialty matrix, such as square matrix, where the number of rows equals the number of columns, and a symmetric matrix, which means the matrix equals to its transpose, and diagonal matrix, where it is square matrix with 0 elements of the main diagonal, and only main diagonal elements are non-zero. And identity matrix is one specialty diagonal matrix, where all ones are on the main diagonal and all other places are with 0. And triangular matrix, which includes upper triangular and a lower triangular matrix. And banded matrix, which means only a band of the matrix is non-zero. Now we introduce matrix operations, starting with addition and subtraction. Matrix addition and subtraction have the following properties. For addition, matrix C equals A plus B. Each element of C, which is Cij, equals Aij plus Bij. Similarly, for subtraction, each element Dij equals Eij minus Fij. And addition also follows the commutative property, which is A plus B equals B plus A. And addition also has an associative property, which means the addition of 3 matrices A plus B plus C is the same regardless of the grouping of the addends. The arranging of the parentheses will not change the results. For matrix multiplication, a scalar G times a matrix A equals to a new matrix D, where each element of D, which is Dij, equals to G times Aij. And for matrix A times matrix B, the calculation is more complicated. Each element of Cij equals the summation of a series of multiplications, and each item of this summation is Aik times Bkj. An example of this calculation is shown here. Cij equals to the multiplication and addition that involves the ith row of A and the jth column of B. For example, C11 equals 3 times 5 plus 1 times 7, where 3 and 1 come from the first row of A and 5 and 7 come from the first column of B. This requires that the number of columns in matrix A must be identical to the number of rows in the matrix B. And the exterior dimensions, which are the number of rows in A and the number of columns in B, define the definition of the result C. One quick question here. When calculating C, can you switch A times B to B times A? The answer to the previous question. Start again. The answer to the previous equation is no, because the calculations will change when you switch A and B. So matrix multiplication is not commutative. But matrix multiplication still has the associative and distributive properties shown in the first 2 lines of this slide. Another matrix operation is to take the inverse. Multiplication of a matrix by its inverse leads to the identity matrix. Therefore, the multiplication of a matrix by the inverse is analogous to division, in the sense that a number divided by itself is equal to 1. Here, we show one example of calculating the inverse of a 2 by 2 matrix, which is A to the power minus 1. Equals 1 over A11 times A22 minus A12 times A21. This whole thing times the matrix with elements A22 minus A12 minus A21 and A11. Similar formulas apply for higher dimension matrix A. However, the calculation will be complicated by hand. It is good that we can use the MATLAB's INV built-in function to calculate the inverse of a matrix easily. Again, the built-in function for calculating inverse of a matrix is inv. Here we talk about another matrix operation called permutation. Permutation is to permutate a matrix by rearranging its rows and/or columns. A permutation matrix, which is also called a transposition matrix, is an identity matrix with rows and columns interchanged. For example, here is a permutation matrix P that is constructed by switching the first and third rows of an identity matrix. Now let's left multiply this permutation matrix and we will get the following. The first and third row of matrix A changed position. Similarly, if we right multiply this permutation matrix to A's first and third columns will change position. And we will have a MATLAB demonstration on permutation. Now we revisit the engineering problem, which is the displacement of the 3 bungee jumpers. Based on Newton's law, we can find the steady-state solution with 3 equations. Here, we use matrix A times vector x equals vector b to replace the original equation system. Then, we left multiply inverse A to both sides of the equation. Because inverse of A times A is the identity matrix, when it multiplies x, the product is x. So we get x equals inverse A plus times b. In MATLAB, x can be solved by using a single line code, which is x equals A left matrix divided by b, or x equals inverse of A times b. You have practiced solving equation sets using MATLAB, so we will not demonstrate this again.